Welcome to the 7th video of this course. So now we'll come back to holomorphic function today. So holomorphic functions. Let me recall the definition what we did few lectures back, and then we look at more examples. Yeah. So we didn't have much examples that time. Actually, there was no example. So today we'll have examples. So definition. So let's first let omega in C be an open set. And definition, a function f from omega to C is said to be complex differentiable we have to define complex differentiable first before going into holomorphic functions. Hence, the function omega from omega to C is said to be complex differentiable if at some point A in omega, if the following limit f of A plus h minus fa by h, as h tends to 0, this must exist. Alright? Exists. And function f omega to C is said to be holomorphic on omega if f is C differentiable at A in omega at every point in omega. Alright, so if f is C differentiable at every point of the open set omega, then f is said to be holomorphic. An example, fz equal to z. Well, fz equal to C, constant function. Constant function is holomorphic, derivative is 0, and here this limit is 1, as you see. Few things to check as an exercise. Sum of two holomorphic functions is again holomorphic. Product of two holomorphic function is holomorphic. Alright? So this implies, so hence this is example 1, example 2, polynomial, a polynomial in Z in Z variable is holomorphic. right? So use this two, and the function f that will give you this. Well, you can take f equal to z to the power n and look at the limits from monomials, and then sum, and the product with constant multiple is again holomorphic. So polynomial is holomorphic. We don't know more example yet, but we want to go into more examples. So what would be the next set of examples that can come here after polynomials? Well, look at, so polynomial is finite linear combination of z to the power n. So you look at infinite series, right? So we want to look at the series of the form a n z minus a power n from 0 to infinity. A j is all complex number. Alright, so we want to look at series of this form. These are called power series. This series is called power series. In z, in z minus a, a power series in z. That's okay. Now, the point is, if you look at an infinite series, then convergence is a big problem. So one has to talk about convergence. What kind of convergence would you like to take? Alright? So we now fix the convergence. Notions of convergence that we would like. So suppose we have some n from, let's say, 1 to infinity, a series of complex numbers. What is our notion of convergence in this case? What we will do, we will define Sn to be summation j from 1 to n aj, and then this sequence is n is the sequence of partial sums if Sj converges, then we say the series summation an converges. Sn, yes, right. If Sn converges, then we say summation an, the series also converges. But we will not take this as the notion of convergence in our case. Alright? So what we would like to take is an absolute convergence. Yeah, so what we need is absolute convergence. So that means a series definition, a series summation n from 1 to infinity converges absolutely if summation mod n converges in this sense, right? So this is actually the definition. This is the definition of convergence of a series. So if we what we consider is absolute convergence, which means a series converges when you take sum of the modulus. All right. So this will become an important player in our case. So now the point is, and look at an example. Summation z to the power n from 0 to infinity, and let's say given mod z is less than 1, z is fixed. So for each z, this for each z mod z less than 1, the series summation z to the power n from 0 to infinity mod z to the power n converges. That means that is summation n equal to 0 to infinity z to the power n converges absolutely. Alright. Now the point is, let's look at a non-example. Let's look at minus 1 to the power n by n, right? So the point is, when it does not converge absolutely but still converges, then the different rearrangement of the series can lead to different limits. So in this case, you can get any real number. For every real number, you will have a representation, rearrangement of this series which converges to that real number. In fact, you can take infinity or minus infinity also, and you have certain rearrangement which will converge to even minus infinity plus infinity. So this converges, but does not converge absolutely. In fact, any number alpha belongs to minus infinity to plus infinity, the closed interval. So you add, so maybe I should write this in a better way, which is R union infinity union minus infinity. There is a representation, rearrangement of this which converges to alpha. Right, so that's it. That's what Riemann's rearrangement theorem, and we don't want this kind of series in this context. In the context when we want to define certain functions for the series. So, and this is geometric series, and this is going to play a very big role in this course. Alright, so now